and grammars. Stack machines versus grammars. There's a lot to be said about stack machines and grammars. You can actually sort of go back and forth using some simple, I would describe them as simple but non-obvious tricks. So these are things that would be hard to come up with on your own, but once you sort of see how it works, it's fairly easy to use these tricks. Non-obvious tricks. I am talking about a method to convert a grammar into a stack machine. So let's talk about grammar to a stack machine. All right, I would like to just sort of do this in an example, and then we'll talk. I think doing the example, it will become clear how it works in general. Let's say this is a grammar that we have, A, B, S, A, or T, and then T goes to B, T, or epsilon. So the language of that grammar, it looks to me like what you have here is balanced ABs balanced with A, and then the thing in the middle can become a bunch of extra Bs. So this makes, as a language, this makes something like AB to the N, B to the K, A to the N. Right? I think that's what this grammar makes as a language. Although that's actually not important to be able to think of it as a stack machine. I would like to try to make a stack machine that copies this grammar. All right. Let's first, before we do that, let's try just an example derivation. Let's derive on the grammar. Just to get a feel for how the grammar works, let's do A, B, A, B, 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 A, A. How about that? All right. This is going to be great. I chose this specific string. So in the grammar, remember how the grammar works. We begin with S, and then we do substitutions one at a time. And if I want to make A, B, well, whatever this is, it begins with A, B. So I better do this line first. S goes to A, B, S, A. So it becomes ABSA. What should I do next? The answer is S goes to ABSA or S goes to T. I think you look at the string and see what you want to come next. I want another AB to follow this first AB. So I better do that first production again. S goes to ABSA. So this becomes... Now it's going to say A, B, A, B, S, A, right? And now this is beginning to look like the string I'm looking for here. The difference is this S needs to turn into 3 B's, right? I have the rest of it all lined up. So now I should make the S go to T. So it'll be A, B, T, A. And now this T goes to BT. I'm going to do that one 3 times. So 1 time, BTAA, that was 1 time. 1 more time, BTAA. 1 more time, ABAB, BBBB. No, that was too many. TAA, and then finally T goes to epsilon, and I'm done. Thank you for your patience in doing this derivation. This will be helpful to explain how the rest of the example works. But this is a typical derivation of a string like that. All right? Now, I'm going to tell you the strategy for converting this into a stack machine. So I am going to make a stack machine. First of all, the alphabet of letters that you read are A's and B's, right? Because my language is just made up of A's and B's. But on the stack, I'm going to use S's and T's from the grammar. All right. So to make a stack machine, we didn't really talk about this formally, but I think you know what I mean when I say it. My stack alphabet, that is to say, the kinds of things that you can put on the stack in this example will be A, B, S, and T. So what you're going to see on the stack is some combinations of S's and T's and also A's and B's. All right? And the way that this conversion works out is the first, each of the grammar productions, there are 4 of them, each of the grammar rules becomes a stack rule with an epsilon read. So each grammar rule is a read epsilon rule on the stack machine. And generally speaking, if it's something like x goes to y, this becomes, on my stack machine, read, pop, push. It's just epsilon x, y. So it's a very simple way to translate the grammar into a stack machine. I said before, this is a non-obvious trick. This is a very simple trick, but it's not immediately clear why this works at all. Each grammar rule, x goes to y, becomes a stack rule. Read epsilon, pop x, push y. Now there has to be more than just that, because these are all read epsilons. You can't have, if your stack machine only has read epsilons, then it's never going to work. But we also make rules for each terminal letter. Remember, in the grammar, terminal means like the little a and the little b, not something which can become something else, but something which ends. We also make rules for each terminal of this format. Read, pop, push. These look like A epsilon, B epsilon, etc. If you have more letters, you would put one of these rules for each letter. All right. But otherwise, that's it. So this is the entire method. You translate your grammar production rules directly into stack rules like this, and then you additionally have these extra sort of read A, pop A, push epsilon. All right. And it all works out beautifully. Can we just see this example? So in our case, in our example, maybe I'll copy that grammar. It's here. Whoa. All right. There's my grammar. So my stack machine looks like read, pop, push. Read, remember how this goes? Each grammar production is an epsilon read. So the first one, S goes to ABSA, looks like read epsilon. Oh, come on. I hate it when people call epsilon E. I just did it. Read epsilon, pop S, push ABSA. There's also read epsilon, pop S, push T. There's read epsilon, pop T, push BT, and read epsilon, pop T, push epsilon. All right? Those are the 4 grammar rules, which I have just translated directly like so. I thought I was going to sneeze, but I didn't. And then I also said read A, pop A, push epsilon. Read B, pop B, push epsilon. All right? Just for now, so that we can talk about these, I'm going to give them numbers here. 1, 2, 3, 4, 5, 6. All right? This is the stack machine. This is actually equivalent to the grammar. I want to try to convince us why this is actually equivalent. I don't want to do a real proof of this, but let's to see why. To do a derivation on the stack machine, I will say copy the grammar derivation. And use rules 5 and 6 whenever possible. And you'll see what I mean when we try it out. Copy the same steps of the grammar derivation, but then use rules 5 and 6 whenever possible. See, when you're actually doing a derivation on this stack machine, it is basically never obvious which step you're supposed to do because they're all epsilon steps. And so it is up to you every time to decide which of these grammar steps you're going to do. And this can be a little tricky, but this is my advice for that. If you're trying to do a grammar derivation, if you're trying to do a derivation on the stack machine, first figure out how to do it using the grammar and then copy those steps in the same order. So my grammar derivation was here. I'm going to try to copy this down too, because you have to sort of follow these same steps. That's what I'm saying. Maybe I can shrink it down a little. Can you still see that? At least a little bit. Oh, I shrank the 6. Okay. So on this stack machine, let's derive the same string, which was A, B, A, B, 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 A, right? On the stack machine, I want to do it. So we begin with that string, comma, comma S, A, B, A, B, 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 A, comma, S, right? On the stack machine. And like I said, I am going to try to do the same steps in the same order. I'm going to start with, I can either do step 1 or step 2, right, on the stack machine at this point, because they're both read epsilon pop S, and I do have S on this thing. I'm going to start by doing step 1, which was the first grammar step that we did. So now this becomes, it's an epsilon read, so the string part stays exactly the same. A, B, A, B, 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 A. And now it was pop S, push A, B, S, A. So the stack now says A, B, S, A. Like that. All right, that was stack machine rule number 1. All right. Copying the first grammar move. Now I said my advice here, to do a derivation, copy the grammar derivation. That is, do the same steps in the same order. And use rules 5 and 6 whenever possible. And actually, one of those is possible now. I have A here and A here. I'm going to do number 5 now, which is read A, pop A. It just says when you have basically an A at the beginning of your string and also an A at the top of the stack, you clear them both, all right, because it's a push epsilon. So doing step 5 now. I read the A on the string part, so now it says B, A, B, 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 A. And then the stack part, the A gets popped and replaced with nothing. So now it says B, S, A. That was rule number 5. All right? And in the spirit of do rule number 5 whenever possible, 5 and 6 whenever possible, we can do number 6 at this point because I have a B and a B. So I see a B, I pop a B. It now says A, B, 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 A, comma, S, A, like that. All right. Generally what this looks like is you do one grammar step and then you do those rules 5 and 6 to kind of clear away some letters from the read string and also the stack. All right. Okay, let's continue then. So I have, I can't do 5 and 6 at this point because I have S on the stack. So I have to do either 1 or 2. Which one is it going to be? You should be inspired by what happened in the grammar. We really only did the first step of the grammar so far. So now I'm going to do the next grammar step, which was again this S goes to ABSA rule. So that's what I'm going to do this time. I'm going to do rule number 1 again, copying the same order of steps from the grammar derivation. So it's an epsilon read, so my string stays the same, A, B, 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 A. But now S, you pop S and replace with ABSA. So now it says ABSAA on the stack part. All right. Great. Now I can do rule 5 to clear the A's and then rule 6 to clear the B's. So I go 5 here, becomes B, 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 A, B, S, A. And then I'm going to do 6 to clear the B's. 1B. I have 3 remaining. B, 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 A, S, A, like so. All right. Getting somewhere here. Now I have to choose a one of the first 4 rules there from the grammar. You should be inspired by which step we did next. Which one should it be? Number 1 or number 2? You can show me the fingers if you like. I see some fingers out there. Let's see. It should be the 2 fingers. Because the next grammar step is this one now. We're only on the 3rd grammar step. But that was the one which changed S to a T. So that was rule number 2 on my stack machine. So it says pop S, push T, read epsilon. Read epsilon means I don't change the string part. BBBAA. Pop S, push T means it now says TAA. All right. What's next? You can't do 5 or 6 at this point because I have a T on the stack. I have to do one of these pop T moves, which is either 3 or 4. Look to the grammar about which move we did at this point. That would be in this step right here. I changed T to BT. So at this point, I should do rule number 3 in my derivation. Number 3. This is read epsilon, so the string part stays the same. T becomes BT. All right, and now I can clear those B's by doing step 5. Or is it 6? 6. Read B, pop B. Like so. Everybody see where this is going? Yes?
Should we like go rule 3, rule 6, like back and forth, or could we go like rule 3 multiple times beforehand?
I think you have to alternate because here's where we get after doing number 3. You cannot do number 6 at this point. I'm sorry, you can do number 6. You can't do 3 again right here because T is not on the top of the stack. Yeah, so you have to do them in that order. So yeah, like he said, we're going to do 3 and then 6 and alternate them to clear off these B's. So that was 3 and then 6. I'm going to do 3 again, which is epsilon read. So it's BBAA, BTAA. Then a 6 to clear the B's. BAA, TAA. One last time. Rule 3. BAA, BTAA. Then a 6. AA, TAA. All right? And now finally, we are at the end of the grammar derivation now. It's this final step where the T becomes epsilon. So I'm going to do that here, which is rule number 4. And pretty much done, although there's a few little. That's what it would look like after you do number 4. And then I do number 5 twice, and then it's really done. All right. 5 gives me AA, and then 5 again gives me epsilon, epsilon. We did it. All right, this is how it goes. I hope you can get a feel for this procedure here. I mean, it's not hard to do. You just do it. But I hope you can get a feel for how this original grammar relates to this these stack rules up here. It involves sort of changing things around on the stack. It's a little difficult to see precisely what is the relationship between, say, these things that you see here, step by step in the grammar derivation. They kind of look like the stack. Like here it's S, and in the next step ABSA, which is exactly the same as in the grammar derivation. Although things get a little weird. Really, what you're seeing on the stack here in each step is kind of the last part of the grammar derivation. It's really the last non-terminal and everything after it on the stack. But anyway, this is how it works. Basically, nothing can go wrong in this procedure. The converting is so simple. I'll just refresh our memory. So any x goes to y becomes epsilon x y, and then any letter a becomes a epsilon. If you can remember that, that's all there is to it, and there's no funny business that can happen in an example like this. Can I have you guys try one? So how about convert this to a stack machine? Really, there's nothing that can go wrong here. All right, and show a derivation of, how about ABAACC on the stack machine. My suggestion would be first make a grammar derivation, because to me that's easier, and then convert that step by step to a stack derivation. See what you think. See this. Oh yeah, there's something wrong with my string. This string is not in the language. I don't know what. No, it is. It is. Yeah. It is.
Oh,
This is
yeah.
not even correct.
I wrote it down.
Because we can do this rule first, which just puts an extra A in the front where it has no weaknesses. So it's not that. I mean, it's hard. It's some complicated thing. Okay. Okay. here. Mm-hmm. All right. Okay. Okay. Huh? Okay. I'm going to write my answer up here. All right, can we chat about them? This is the stack machine as I wrote it. I think pretty much there's not any debate about that part. I mean, you just do what I said to do in terms of translating step by step the grammar into a stack machine. Now, how do I make a derivation of this particular string? I would suggest you write down a grammar derivation of that string, which I did here. Now, I did this first rule first, S goes to ASC, although there are other ways that you could have done the grammar derivation, which would lead to different stack derivations also. But this is how I did my derivation on the grammar. And so on the stack machine, it looks like ABAACC, comma S. So first I do rule number 1, I guess. It will say ABAACCASC. And then I clear the A's, BAACCSC. All right, and now I have a B and an S. So, well, that's not important. I'm going to do one of these epsilon moves. The next grammar move I made was S goes to BS. So that is going to be step 3 in my stack machine here. So this will be BAACC. BSC, and then clear the B's, AACCSC. All right. Now I am going to do next, the next step that I did was S goes to AS, so I need to do that step, which is the second one on the way that I wrote it on my list. It's now AACCASC, and then I clear the A's, ACCSC. Am I doing okay so far? I think so. Now I do S goes to ASC in the grammar, which on the stack gives me ACCASCC. And then I clear the A's. I got CCSCC. And now the last grammar, this is the end of the grammar derivation. It goes S to epsilon. So that just clears the S. CC, right? And now I do whatever my last rule twice to clear everything away. CC, and then epsilon. The end. I hope you did something like that. This will take you a few minutes to write down all the details, but I think there's really not much at all that could go wrong when you're doing this kind of a thing. All right? I hope that you agree. Great. Can we just talk a little bit, slightly abstractly, about what this all means? So, when does this work? The answer is basically always. I mean, I keep on saying nothing could really go wrong here. Although, one thing to notice, we go, the basic method is X goes to Y in the grammar becomes epsilon X, Y, right? Read, pop, push. Now, I didn't make a big deal out of this. I never said precisely what is allowed in a stack machine. But when I ask you, for instance, when I say when does this work, really the question I mean is for which grammars will this method actually work? And you may be tempted to say, well, this will work for any grammar, because what else could happen? It's not like, in a calculus class, you always worry about what if I divided by 0 or something. But there was no step here which involved anything that could go wrong. Really what you should be wondering is, what am I actually allowed to put in the pop column, and what am I allowed to put in the push column of a stack machine? And the basic idea, the concept of a stack machine is that it is only capable of accessing the top element of the stack, all right? And what that means is the pop here, this must be a single stack letter. All right. In every example we've ever done, and this is true, if you were doing the homework problems correctly, you're not allowed to put a more complicated string in the pop column. It can be in the push because you're allowed to just push several things onto the stack, but the stack can only be accessed on the top. You're not allowed to pop something deep into the stack, and you can't pop a whole string off the top. You can only pop a single letter at a time. All right. This must be a single stack letter. So what that means is this method will only work when the X in the grammar is a single letter, all right? Because if it's not, then you end up with a stack machine which is not allowed, okay? So this works, this whole thing that we've been doing here, this method works for any grammar in which all steps look like X goes to Y, where X is a single letter. You're not allowed to have more than one thing on the left side of the arrow. Actually, we already have a name for that. What were you going to say? Yeah, what is it?
Context-free.
Yeah, this is the definition of a context-free grammar. This is one of the reasons why I was talking about focusing on context-free grammar so much. So this method works for, I will say, i.e., it must be a context-free grammar, which is basically every example that we've ever done. That's not quite true. I mean, it's easy to write down examples of grammars which are not context-free, but context-free, remember, means the left side of the arrow is just a single letter, a single non-terminal, all right? It must be a context-free grammar. But anyway, this is still sort of a lot of things, right? A lot of languages can have context-free grammars. All your like A to the N, B to the N, something like that has a context-free grammar, okay? So really what we've demonstrated here is that any context-free grammar can be converted to a stack machine. All right? And now, I mentioned at the beginning some of the stuff that we do today might be helpful in doing the homework for tonight. Now you may realize what I mean. If somebody sort of approaches me at the club or something and asks me to create a stack machine for a particular language, to me, the easiest way to do that is to make a grammar and then convert it to a stack machine. I find that to be much easier than just trying to invent a stack machine out of nowhere. Because, I don't know, I find it easier to make a grammar for something. Like if I just give you, one of the homework problems is this, A to the N, C, B to the N. Even just doing that, a stack machine for that, I find to be not exactly easy. I mean, it's not super hard, but to me, that's easy to make a grammar out of because I can understand I have the A's balanced with the B's and the C ends up in the middle. So to me, it's a lot easier to make a grammar for that and then convert it to a stack machine in this way. All right. So this is actually a very sort of, I would say, powerful method, right? This allows you to make stack machines for things which otherwise might seem very complicated. All right, let's discuss what about the other way around. Can you convert a stack machine back into a grammar? Well, this also has what I would describe as a fairly simple but non-obvious trick. So let's talk about, what about stack machine to grammar? Again, there is a simple trick. It's not at all obvious. It would be hard to come up with this on your own. And even once somebody shows it to you, it's hard to really understand why it works, but it does work. And I'll try to talk about why it works. But yeah, stack to a grammar, you can also do this. It's very simple to describe. Here's how you do it. Any stack rule that looks like read, pop, push. This I would encourage you to just remember. If it says X, Y, Z like that, this becomes a grammar rule. Y goes to X, Z. And that's it. This is the foolproof way to convert a stack machine back into a grammar. As I said before, it is not at all obvious why this works, but it is my goal in the next 20 minutes or so to convince you that this actually works. All right. But anyway, let's just try an example first, see how this really goes in practice. I have a fairly complicated stack machine here. Read, pop, push. This is actually our maybe last time, maybe the time before, was an example that we talked about. This is a stack machine for all strings having the same amount of A's and B's in them. Read A, pop S, push SX. Read A, pop X, push XX. The idea is the stack counts how many A's and B's there are. If there's extra A's, it pushes a X. If there's extra B's, it pushes a Y. And if you see an A and a Y, then they cancel because a Y represents an extra B and an A is an A, and you want the number of A's and B's to be equal. So you make them cancel. All right, and then the B rules are similar, but kind of the other way around. So it's B, S, S, Y, B, Y, 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 and B, X, epsilon. And then just as a technicality, to get rid of the S at the end, you go epsilon, S, epsilon. All right, so this was a stack machine. It's not really important that you know what it does, but this is a stack machine for all strings where this the number of A's is equal to the number of B's. All right, and now let's convert this to a grammar, just doing what I suggested before. You can still almost see it on the top there. Any rule, X, Y, Z becomes Y goes to X, Z. So converting this to a grammar, I'm just going to try not to think about it and just write it down. X goes to A, X, X. Y goes to, I guess, just A. You always do the middle guy, the arrow, and then the left guy and the right guy. S goes to B, S, Y. Y goes to B, Y, Y. X goes to B. S goes to epsilon. That's it. This writes everything as sort of individual steps, but of course we would more typically write this sort of collected together. S goes to ASX or BSY or epsilon, right? X goes to AXX or B, and Y goes to A or BYY. This is my grammar. And I would like to try to convince everybody that this really is the same as the stack machine. Like I keep on saying, in my opinion, it's not at all obvious that this works. It seems kind of too easy to actually work, but it really does. All right. maybe to convince ourselves that this is a legitimate thing that really works, let's try to do a derivation of, let's try ABBA. This is a simple string, which does have the same number of A's and B's, so I expect that this you can derive on the stack machine. Let's try it on the stack first. I want to just compare the stack derivation versus the derivation using that grammar on the right. And you'll see that there are some relationships. So anyway, the stack derivation. I begin ABBA, comma S. All right, which step should I do? I think actually there's only one step to do at this point. It's the first step on the stack machine. Read A, pop S, push SX. So I'm going to do that one. Maybe I'll put numbers. The numbers. 3, 4, 5, 6, 7. So this is step 1 I'm doing first. BBA SX. Right? That was a read A, pop S, push SX. What next? Actually, in this stack machine, there's not a lot of opportunity for making the wrong choices. I have I'm reading a B and I have an S on the stack, so I should do rule number 4. Read B, pop S, push SY. Number 4 says, so I read the B, so the B disappears, and now the stack says SYX. All right? Next, I have a B and an S, so I guess I should do rule number 4 again. Now it'll say A, S, Y. Sorry, something's wrong here. Oh, can you believe it? I'm ashamed to say it. I wrote, this is terrible. I wrote these wrong. This SX should be XS. That unfortunately ruins everything. Sorry about this. So this is XS. This is YS. In this stack machine, it keeps the S on the bottom of the stack, not on the top. So that means this is XS. Oh, I'm so embarrassed. This is the kind of thing I want to do after you've all done the course evaluation forms, not before. So here, all right, I just have to change this everywhere you see it. A goes to XS, B goes to YS. That's it. And so it didn't matter until now when I find this S on the front of the stack. So this should say, I'm just going to redo it from here. Sorry about that. This should now say BBA YS, right? Not SY. Now my pen's losing it. Sorry about that. All right. Now I have to do rule 5 next.
Isn't it X? Yeah, isn't it XS?
X? Oh, because this was an A. Yeah, thank you. X. Now I don't know what's happening. So it's not rule 5 that I want to do. It's rule 6, I suppose. Yeah, because B is supposed to cancel an X on the stack. Yes, it's definitely rule 6. So now it says BA, comma, S, right? I think I'm back to where I want to be now. Next, I have read B, pop S. That's rule 4. Gives me A and then a YS on the stack. And then I have read A, pop Y, which is rule 3, which makes it just A, comma, S. Sorry, no A anymore, right? I read the A, so it's epsilon S. And then finally, I'm trying to stick this all on one line. Sorry, I'm going off the side here. Because I want to put the grammar derivation right underneath. You'll see some similarities when we do it on the grammar. Finally, we get to epsilon, right? So this A goes to A, read A, pop Y. That was rule 3. And then read epsilon, that was rule 7. All right. So this is the stack derivation. I would like to write a grammar derivation for the same string, and hopefully we'll be able to see some commonalities towards the end of convincing everybody that this stack machine and that grammar really are the same thing. That's my goal here in lining these two derivations up together. I'm trying to explain why the stack machine and the grammar really are doing the same thing. So if I were to derive ABBA on the grammar, you can kind of match these same steps. So step 1 here was read A, pop S, push X, S. I'm just going to do the corresponding grammar step, which is S goes to AXS. So I begin with S, and then I say AXS. I'm trying to line these up sort of right under each other with the corresponding steps, right? S goes to ASX. Next on the stack machine, I did 6, which is this one, which apparently is X goes to B. So I'll do that on the grammar. All right, X goes to B. It now says ABS, right? Next, on the stack, I did 4, which is BSYS. So I'm going to do S goes to BYS, okay? S goes to BYS makes it ABYS, all right? I'm doing the same steps in the same order. Next on the stack was rule number 3, which is AY epsilon, which is Y goes to A, so I do that. This becomes ABAS. And then finally, rule 7 was epsilon, S epsilon, which is S goes to epsilon. What happened? Did I skip a step?
It should ABB.
ABB, yes, thanks. I wrote an A, I should have wrote a B. Yes, Y goes to B, is that? Why does it say Y goes to A?
No, it should be, for the second one, it should be A, B,
This is
B,
a-
Y.
Because
it goes to BYS.
BYS.
Yes, I left out a B here. Thank you. Sorry about that. ABBYS. So now it's ABBAS. Right, and then finally S goes to epsilon. ABBA. Okay, thank you for that. It's getting too hot in here. It gets hotter every time I mess it up. All right. Okay, what are the similarities between these two derivations? Do we see any similarities or differences? Any thoughts? Yeah.
It's going like the opposite direction.
Yeah, you kind of feel like, I feel like at least, the grammar starts from nothing and creates the string out of nothing, whereas the stack machine kind of starts with the whole string and eventually eats it up to nothing at the end. Yeah, I would agree with that. So there's, in a sense, they're kind of opposites. I don't know. You might imagine reading this one backwards and getting that one. Oh, it's not quite like that. Anybody see any other kind of connections here? Yeah?
Are they always going to have the same number of steps?
Yes, they will. Yeah, you can do exactly the same steps in the same order, and it'll always work out. Yeah, that's definitely true. I see another thing. If you look at just the stack part here, in each step, just look at the stack. Actually, I can see that down here. Those things exist. They're always just kind of at the end in the grammar steps, right? The stack appears down there. So the stack is on the end. What appears in front of the stack each time? Can you make some kind of relationship from each step? I don't know. Does anybody see? Like here in front of the stack is nothing. Here it's A, then AB, then ABB. Anybody?
That's
Yeah.
what you've already read.
Yeah, what you see before the stack here is the part of the string which has already been read, which you don't see in the stack derivation because you stop writing it when you read those letters. Okay, but anyway, I'm going to try and summarize this. So each grammar step, like while you're doing this, while it's in progress, each grammar step looks like the string which has been read so far. It's the portion of the string which you already read, followed by the stack, right? That's always what it looks like. This is the one I underlined in red. The rest of it is just the portion of the string which has already been read so far, all right? And can we say what actually happens to the string from one step to the next? So when we do a stack step that looks like, read X, pop Y, push Z. What is the effect of that in the grammar derivation? So first of all, when we do a stack step like this can only happen if Y is on top of the stack, right? Because otherwise you can't do that rule. If the rule says pop Y, you only do this rule when Y is on the top of the stack. And the effect of that is that X now, after you do that stack rule, you read the X, which in the context of the grammar means X joins the string, the parenthetical portion, string read so far, right? X joins the string read so far because we just read the X when you do that rule. And Y leaves the stack and is replaced with Z. Right? That's because you're popping Y, you're pushing Z. All right? And so all of this means, if I were to write down precisely what happens in the grammar, all of this looks like this. It looks like some stuff here. This is, well, I'll just say the string read so far. I'm just getting to the good part. All right? Like I said, the only way you can do this rule at all is if Y is on top of the stack. So look up here, what these pieces look like in the grammar every time is the string read so far followed by the stack. But this is only going to work if Y is on top of the stack. So it has to be a Y there and then followed by the rest of the stack. Right? And then what happens when you actually make the changes according to the stack rule? I said, the effect is X joins the string read so far. So what you see now is the string part, now followed by X, right? It didn't used to be there, but since you read an X in this step, you have to add the X into that part of the string. And then Y leaves the stack and is replaced by Z. So then it will be Z followed by the rest of the stack. Right? The X, which didn't appear before, now enters the string, which is read so far. And then the Y changes into a Z. All right? But now I think it becomes clear that this is Y becomes XZ. This is what I've been trying to build up to this whole time, all right? When you do one of these stack lines, it has exactly the same effect as replacing Y with XZ. And that's why this whole thing works. Because it's the same as Y goes to XZ. All right? As with many sort of proofs in math, you don't actually have to remember this reasoning in order to make it work when you're doing examples. But this is why this whole procedure works properly. All right? Any thoughts about that? So what we have said so far is you can convert a stack machine into a grammar in exactly this way, right? X, Y, Z becomes, just remind you one last time, Y goes to XZ. And I will say, remember what I said a little while ago. In a stack machine, this Y is required to be a single letter, right? A single stack symbol. And what that means is if you do this process, this grammar that you get will automatically be context-free. The Y is guaranteed to be just a single letter because it came from the pop column of a stack machine. And those have to be just a single letter. So this Y, this will always be a single letter. And so the grammar we get is a context-free grammar. All right? And so what we've seen, the sort of first half of what we talked about today was you can convert any stack machine to a context-free grammar. And now this says you can convert any, sorry, I said it backwards. We started by saying you can convert any context-free grammar to a stack machine. And now this says you can also convert any stack machine back into a context-free grammar. What that means is all the languages, the language of a stack machine, it is the language of a context-free grammar, and the other way around is also true. All right, so the set of languages, I'll write this like a theorem. It follows from these two constructions that we've talked about. L is the language of a context-free grammar if and only if L is the language of a stack machine. They are the same category of languages. All right? Because you can interchange them back and forth. You can change a stack machine to a context-free grammar, and you can change a context-free grammar back into a stack machine. So these must be the same category of languages. All right? So this is similar, you can tell your friends at dinner tonight. You can say, hey, remember how I told you that all the NFAs and DFAs, those make the regular languages? Well, now I know. All the stack machines, that's what makes the context-free languages, right? This is the category of context-free languages. The machine for them is the stack machine. And the category of regular languages, the machine for them is the NFA. All right? Great. This is getting to be the end of what I want to say about context-free grammars and also stack machines. So this is, I will just remind us of this sort of picture of languages, which we call the Chomsky hierarchy. There's the regular languages, which are the simplest possible ones. Not the simplest possible, but they're the simplest ones that we ever talk about. Like A to the N is a regular language. And then there's a larger category of context-free languages, CFL, which includes A to the N, B to the N. All right? Another way to think of this is the regular languages are the NFA ones, and the context-frees, those are the stack machine languages. All right? And then as I've said before, our real goal for the rest of the course then is to talk about what is outside of the context-free language domain. These are languages which you cannot make using a context-free grammar. And maybe we got 15 minutes left. We can begin a discussion of that. What about non-context-free languages? All right. It is tempting to say a non-context-free language would have to be very, very weird, but actually they don't. There are some fairly ordinary-looking ones that are not context-free. And the standard example of this, is A to the N, B to the N, C to the N. Somebody asked about this a couple weeks ago. How can you make a context-free grammar for that? The answer is actually you can't. It's not entirely obvious that this is not possible to do with a context-free grammar, and I don't really want to get into this. There is some, to show something's not regular, you can use derivatives. As far as I know, there's not a similar kind of derivative type way of showing that something is not a context-free language. If you ever looked in the book, you will notice that our book actually doesn't discuss derivatives at all. They use something instead called the pumping lemma. I don't know if you ever saw this. There's a whole chapter in the book about the pumping lemma. I know at least one of you tried to do the homework from that section, and you had not been in class, and so you're trying to do the pumping lemma. The pumping lemma is, in my opinion, kind of clunky, and I like doing it with derivatives much better. There is something called the pumping lemma for context-free languages, which is also in the book. You can check it out if you're interested. This is a way that this is a special kind of abstract trick that you can do to show something is not a context-free language. I would rather not spend the time on that. It's not beyond our abilities, but just because I want to get to the Turing machines, I hope you won't mind if we skip this. So this is not context-free, but I'm not going to try to prove it. If you want to prove this, like I said, I'm not aware of a method to do that using derivatives. You have to use the pumping lemma for context-free languages, which I don't want to get into. Anyway, I thought instead of doing a real proof of this, I would show you. So everybody knows if you want to have only two things balanced in a grammar, you can do that with a context-free grammar, right? If it was, everybody knows, A to the N, B to the N, you do S goes to A, S, B, or epsilon, right? You might try A to the N, B to the N, C to the N. How could you make that happen? Well, one way would be maybe this. Would that make it? No. Can somebody say, actually, you can say without too much trouble, what language do you get from that? Or what's the problem? Yeah.
A to the N, B, C, T to the N?
Yeah, this makes A to the N, B, C to the N, which is that's not what I said. I want A to the N, B to the N, C to the N. Yeah.
Would AS, BS, C now?
Okay, so this was a bad idea. This is a better idea, maybe. It's still not going to work, but A, S, B, S, C. How about that, huh? How you like me now? If you just try a couple steps, you will immediately see that this also doesn't work. So if I do something like S goes to A, S, B, S, C, and then maybe turn the first S to an epsilon, but do the same rule for the second S. It now says A, epsilon, B, A, S, B, S, C, C. I think I did that right. Now if you turn those S's into epsilons, it looks like A, B, C, C, which is not what I want, right? The thing is this doesn't keep the A's and the B's all separate from each other, because when you put this S here, it allows you to, in the next step, insert an A after this B, which messes it all up, all right? So this, unfortunately, also does not work. You may find yourself wondering, can you even do this language at all, like with any grammar at all? Actually, it is possible. Here is a grammar for this language. It's not going to be context-free, though. A grammar for A to the N, B to the N, C to the N, just to show sort of what is actually required to make this work at all. Here's one way you can do it. S goes to A, S, big B, C. The idea here is the big B stuff is going to turn into little b's eventually, but in a slightly weird way. Just as a technicality, I have to put A, B, C, or epsilon here. Those are not so important, but technically to make it work. The problem is, like, you need to allow, like, this B is going to turn into little b's, but this S, when you do this step again, is going to create a C to the left of this big B, which is a problem because you don't want any C to the left of a little b. And so that's why we use a big B there, and then we have a special rule, CB goes to BC, like that. This allows you to do the first rule several times and then move all the little c's to the right past the big B's. And then, of course, like I said, every big B turns into a little b, like that. All right. This is a grammar. So this allows you to derive, for instance, if I want to derive A, B, B, C, C, I would go S goes to A, S, B, C, and then do it again. A, S, B, C, B, C, right? And then I interchange the order of the B, C, right here. These guys I swap using that weird middle rule there. So it now says AAS, big B, C, C, right? I swapped the B and the C. And then I can make the S epsilon and make the two B's into little b's, and everything is done. AA, BB, CC. All right? So it really does work, but it requires this line right here, which is not context-free, right? That's what I'm trying to say here. That, the use of that grammar step means that this is not a context-free grammar. And in fact, you'll just have to take my word for it. It is not possible to do this with any context-free grammar. All right. So you could add this onto your little chart out here. A to then B to then C to then. That's an example of a language which is outside of the other two categories. All right. We have one last thing to say. This is really all that we are going to say about stack machines and context-free grammars. After the little break, we will start talking about Turing machines, which is what we're going to talk about for the whole rest of this semester. The most complicated type of machines. But I thought I would just say one last thing, sort of a real-world example. I mentioned often, like, real-life programming languages can be described using grammars. We looked at the Python grammar, I don't know, last week or something. Many programming languages, including Python, actually is in this category. If a language requires balanced, or yeah, I'll say balanced. It's not really the word that I mean, but indents, right? In Python, you have to indent properly, and if you don't, then you get errors, or it does something different from what you wanted. Every block of code in Python has to be indented to the same level, and the indentation is meaningful, right? The other languages are not like this, but Python is like that. If a language requires balanced indents, that means the code looks something like, let's say this is like the side of of your code window. You have some stuff here, and then in Python it's like a colon, and that means you're going to indent the next stuff. These T's represent tabs, because that's how you indent stuff, right? And then maybe after that you go back, which in Python they call a dedent, but there's no button on the keyboard to make it dedent, but that's what they call it. All right. Or you could have a block, of course, maybe this continues with a tab, and then maybe a few lines with two tabs, right? Etc. Right? This is what a legal Python block looks like. It has this kind of uniform indentations, all right? But I will point out, any kind of block, so blocks at the same indent level, by that I mean like these two lines here, they're both indented twice, right? And they have to, blocks that are next to each other, they have to be indented to the same amount. Blocks at the same indent level must look like something like T to the N, something, 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 T to the N, something, 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 T to the N, something, 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 right? What if I were to just write these blocks without the line breaks? What it looks like is some amount of tabs followed by some stuff, followed by the same amount of tabs and then some more stuff, and then again the same amount of tabs and then some more stuff. All right? Such a language cannot be context-free because of this sort of 3 times repeated matching exponent here. All right? What this means is the Python programming language is not a context-free language because it does allow for this kind of several blocks in a row at the same indent level. And the compiler or the interpreter, before you try your code, it will actually verify that the indentation levels are matching. And in order to do that in more than 2 positions, it has to be a non-context-free language. So this means, that Python can't have a context-free grammar, all right? And this, you should maybe be a little concerned, like perhaps you remember, about a week and a half ago, I showed you the context-free grammar for Python. So what's up with that? really, this has to do with the fact that in that grammar, it says dedent, which that's not actually part of the language. Like your file doesn't have a dedent symbol in it. But the dedents in the grammar can be used to kind of cancel these out, and then things work out okay. But it is technically true that that grammar is not technically context-free because it involves some kind of trickery. It's mostly context-free, but not entirely because of this kind of balanced indenting issue. The same issue is not true of balanced parentheses because the only balancing in parentheses is one end with one end. There's no such thing as like there's only two things that have to match. There's not three things that have to match. So balanced parentheses is no problem at all for context-free, but balanced, this kind of arbitrary matching indentation levels, as many as you want, that's a problem for context-frees. All right, I think that's enough to leave it at that. So next time will be Turing machines. And I hope you all have a great little break.